Welcome back everyone. In this lecture we will continue with the basic theory of Lie algebras. We will now define the direct product. So, let us begin with two Lie algebras G1 and G2. So, let G1 and G2 be two given Lie algebras. So, then take their Cartesian product G1 cross G2. So, this is set of all tuples x comma y where x comes from G1 and y comes from G2. So, now using the Lie brackets on G1 and G2, we define Lie bracket on G1 cross G2 as follows. The bracket x1 y1 comma x2 y2 is defined to be the bracket x1 x2 in the first coordinate comma the bracket y1 y2 in the second coordinate, and this is true for all x1 x2 comes from G1 and y1 y2 comes from G2. And it is easy to check, this defines indeed Lie algebra structure on G1 cross G2. So, moreover, we have the following informations. So, if we take the center of G1 cross G2, then it is easy to see that it will be the product of the individual centers. And similarly, if we take the derived algebra of G1 cross G2, so this will be a product of the respective derived algebras. You take the derived algebra of G1 and then the derived algebra of G2, take the product, that will be the derived algebra of G1 cross G2. And also if we take G1 cross 0 and 0 cross G2, so both of them will be ideals inside G1 cross G2. And it is easy to see if we go modulo G1 cross G2 modulo this first ideal G1 cross 0. So, that will be isomorphic to G2, and if you go modulo 0 cross G2, then that will be isomorphic to G1. So, all these things can be easily proved. So, I will leave it to you to check. So, this is actually called external direct product. So, we can also define what is called internal direct sum. Okay. So, the direct sum is defined as follows. So, the direct sum of subalgebras, okay. So, G is said to be direct sum of G1 and G2, both of them are subalgebra of G. So, if it satisfies the following condition. So, you start with G, which is a Lie algebra, and then let us say G1, G2, both of them are subalgebra of G. Then we say G is a direct sum of G1 and G2 if the following satisfied. So, if we take G, then that should be equal to G1 plus G2. So, that is the first condition. The second condition, G1, G2, both of them must be ideals inside G. The third condition, whenever you write x plus y equal to 0 for some x in G1 and y in G2, then we must have x equal to 0 and y equal to 0. So, this means given any element of G, that should be written as uniquely as sum of element from G1 and element from G2. Okay. So, there are various equivalent version of direct sums. Okay. So, one can take this as definition, no issue. So, now there is a close relationship between direct product and direct sum as long as you consider finite direct products and finite direct sum. And once we have the definition of direct product of two Lie algebras, it is easy to extend that to any finite direct products. Similarly, it is easy to extend any finite direct sum. Okay. So, now I will leave it as exercise that if you have direct product of two Lie algebras, then it will be naturally isomorphic to direct product of two to Lie subalgebras. Okay, let us start with G, Lie algebra, and G1, G2, both of them are subalgebra of G. Okay. So, then one can define natural map from G1 cross to G2 to G if it is a direct sum of G1 to. So, let us say G1 G2 chosen subalgebra such that G equal to G1 direct sum G2. So, then you can easily see that this map x comma y goes to x plus y defines an isomorphism between G1 cross G2 to G. So, this is something easy to verify. I will leave it to you to verify. So, now we will actually get back to GLN and SLN and understand its structure. Okay. So, let us recall some of the things. So, what is GLN? So, GLN is the set of all n by n matrices, the set of all n by n matrices. So, in particularly we have this standard basis Eij where ij less than or equal to n. So, this is the standard basis of GLN. In particularly the dimension of GLN is n square. Similarly, we have SLN which is traceless matrices inside GLN. So, now we have this natural basis. So, you take Eij I not equal to j which comes from 1 to n and the disjoint union the Hi's where I range from 1 to n minutes, where Hi defined to be the diagonal matrices Eii minus Ei plus 1 I plus 1. So, basically it looks like pictorially 1 at the ith place and minus 1 at I plus 1th place. All remaining entries are 0. Okay, that is Hi. And it is easy to verify this is the basis of SLN. So, now using this we will determine the structure of GLN and SLN. It is easy to see that GLN is direct sum of SLN and this one dimensional subspace which is indeed ideal inside GLN, which is spanned by the identity matrix IN. So, IN is the n by n identity matrix. So, in terms of basis, this is nothing but the summation Eii where I range from 1 to n. So, now one can easily check this GLN is direct sum of these two subalgebras, okay, because this IN is indeed sits inside the center of GLN. So, we can prove it is indeed equal to the center. Okay. So, here is the claim, the center of GLN is exactly one dimensional space spanned by the identity, and if we take the derived algebra of GLN, so that is going to be exactly equal to SLN. And moreover, one can also determine all the ideals of GLN. The ideals of GLN are the trivial spaces 0 and GLN, and on top of it you have the center and the derived algebra, and that is all, nothing else, because SLN has codimension 1 there. So, there is no other subspace, proper subspace that contains SLN inside GLN, and there is no proper subspace of center as well, because the center is one dimensional, and these are all the only ideals of GLN. Okay. Now, using this one can actually verify that SLN must be simple algebra. In particularly, the center of SLN must be trivial and the derived algebra of SLN must be itself, and moreover the only ideals of SLN are 0 and ideals of SLN are 0 and SLN. So, that means SLN is simple Lie algebra. So, this is the only simple Lie algebra that we will be encountering in this course. So, we will be mostly focusing on GLN and SLN in this course, no more other Lie algebras. Okay, so let us prove one by one. So, we will actually begin with understanding the center. So, let us start with proving the center of GLN is the identity. Okay. So, it is clear that identity lies in the center. So, now you start with x being in the center of GLN, then it is immediate that the bracket xy is 0 for all y in GLN. That means x and y commutes for all y in GLN. Okay. So, since we are working over complex numbers, we can make use of the eigenvalues and eigenspaces. So, let us say that we want to prove x is nothing but some lambda times identity. That means it has exactly one eigenspace with eigenvalue lambda. Okay. So, let lambda be an eigenvalue of x, which exists because we are working over complex numbers with the eigenspace. So, eigenspace by definition must be non-zero eigenspace, which we denoted by V lambda. So, this V lambda must be non-zero. Let us say we have at least one vector V, which is non-zero vector inside V lambda. Now, since x commutes with any operator y, okay, if we take this eigenspace V lambda, it is clear that this eigenspace V lambda must be invariant under y as well. Okay. For any y inside GLN, it is clear that y of V lambda must be subspace of V lambda. So, that is because if I take x w, which is lambda w, okay, for some w in V lambda, then it is clear that x y w will be y x w, which is exactly equal to lambda y w. So, this simple calculation tells you that y w must be again inside V lambda, and this is true for all operators y. Now, given this vector V and given any other vector, okay, choose any vector w inside Cn. So, then we can have an operator again y inside GLN such that y maps V to w. Okay. So, let us say fix this vector, then choose y inside GLN such that y of V is w. So, now y of V lambda is subspace of V lambda, that would imply immediately y of V, which is w, is inside V lambda. So, that will imply that entire Cn. So, because this is a n dimensional, it is acting on n dimensional space. So, this entire Cn must be subspace of V lambda. So, that will force that V lambda equal to Cn. So, that means x is acting as lambda on entire space Cn. So, that means x is exactly lambda times identity. So, that is what we wanted to prove. So, any element inside the center of GLN must be scalar multiple of identity. So, now we will check that the derived algebra must be SLN. So, if we take GLN the derived algebra, so that must be SLN. So, one way is obvious, because for any x and y inside GLN, the trace of the bracket xy must be exactly equal to trace of xy minus yx, which is exactly equal to 0, because trace of AB is same as trace of BA. So, that implies that if I take this derived algebra of GLN, that must be contained in SLN, there is no other option. Now, we will show that any element of SLN must be contained in the derived algebra. Okay. So, for that what we will do, we will verify that all basis elements of SLN must lie inside the derived algebra. So, let us start with Eij and I not equal to j. So, this is one of the bases. Then it is easy to see that. So, this must be exactly the bracket of this Eii comma Ejj. So, which is nothing but the product Eii Ejj minus Ejj Eii. So, now you can easily see that. So, this bracket, sorry. So, we want to prove that SLN is actually contained in. So, what is the claim? The claim is SLN is contained in the derived algebra. So, now you take this basis element Eij, then you can easily see that this is exactly. So, maybe I should put. So, let us work it out. So, if we take E ij times Ejj, so that is going to be Eij, and then minus Ejj, Eij will be 0. Yeah, so this is going to be just this thing. So, this is exactly Eij Ejj minus Ejj Eij, which is exactly Eij. So, recall that Eij Ekl is going to be delta Jk Eil. So, this is the product formula. Okay. So, in particularly Eij can be written as the commutator of two elements. So, that is all we want. So, now if we take the other type, which is Hi, which is nothing but Eii minus Ei plus 1 I plus 1, then it is easy to see that this is going to be the bracket Ei I plus 1 and then Ei plus 1 Ei plus 1 I. So, this is going to be Ei plus 1 times Ei plus 1 I minus Ei plus 1 I times Ei plus 1. So, which is exactly equal to Ei minus Ei plus 1 I plus 1. So, that means this is both these elements are inside the derived algebra. Okay, that proves that all the basis elements of SLN lies inside the derived algebra. So, that means we have that this SLN sits inside GLN. So, we have that the derived algebra of GLN is equal to SLN. So, now let us actually try to understand all the ideals of GLN. So, now if we take some ideal of GLN, then we want to claim that must be one of the 4 ideals. Okay. So, let us call it a theorem because it is a very important result. So, the ideals of GLN are the 0 identity SLN or GLN. So, these are all the only ideals. So, now you can see that this is nothing but the center and this is nothing but the derived algebra and we do not have anything more. Okay. So, let us start with I being ideal inside GLN. So, we have to consider some cases to prove this. Okay. So, let us assume that it is a non-zero ideal. If it is 0, then there is nothing to prove. Okay. So, basically what we want to prove that since SLN has codimension 1 and the center C times identity that has dimension 1. So, if we prove that either I is contained inside the C times identity or I actually contains SLN, then we are done. Okay. So, we claim that either I is contained in C times identity or I must contain SLN. Okay. So, how are we going to proceed? We actually further assume I is indeed contained in the what is called a set of all diagonal matrices. So, let us denote dou n by the set of all diagonal matrices of GLN. Okay. So, now consider the case. The case 1, let us say that I is contained in dou n, suppose. Okay. So, in this case we claim, okay. So, in this case we claim that this I must be contained in C times identity. So, there is no other option. Okay. So, now how one can actually proceed. So, suppose I is actually not contained in this C times identity. Okay. If I is not contained in the span of identity, so then there exists some element x which will look like summation akk ekk where k range from 1 to n inside I, but this will not have all the entries, akk will not be same. So, that means, so there exists this element with the pair I not equal to j such that this ai must be not equal to ajj. So, with the coefficients ai, ajj distinct, we can have inside x. So, now it is easy to do the following computation. If you take the bracket x ejj, then you can easily see that this will be exactly aii minus ajj times eij, and this has to be inside I because I being ideal. Now, ai is different from ajj, that means this coefficient is non-zero. So, this coefficient is non-zero. So, that would imply that eij must be element inside I. So, there is no other option. So, now I to begin with we assume that is subspace of the set of all diagonal matrices, but we have produced one element eij where I is not equal to j inside I, and this is a contradiction to our assumption. Okay, this is actually a contradiction to our assumption that I is contained in dou n. So, that proves I must be, so this proves I must be contained in C times identity. So, what we have proved so far, if we assume I is contained in dou n, then that implies I is contained in C times identity. Okay. So, that means if I is not contained in C times identity, then it implies I cannot be contained in dou n. Okay. So, here is the case 2. Let us assume I is not contained in C times identity. So, if I is contained in C times identity, then we are done. So, let us say I is not contained in the one dimensional space spanned by identity. Okay. So, then that would imply that I is not contained in dou n. So, that means there exists x which is denoted by let us say some a k l e k l where k l varies over 1 to n. So, which is inside I, and what the condition that we have for this AKL, at least for some pair I not equal to j. Okay. So, there exists a pair I not equal to j such that this ai j is non-zero for some I not equal to j. Okay, let us actually play with this aij and then get what we want. So, now we are going to compute eiix. So, it is easy to compute using the formula. Then you can easily see that this is going to be exactly equal to summation over L AIL EIL minus summation AKI EKI, where the second sum runs over K. Now, if you do one more computation, that the bracket EIIX comma the bracket EJJ. So, then you get exactly AIJ EIJ plus AJI EJI. Now, if we do again one more hit with add of EI, so which will give you that, let us call this some element y, then the bracket EII y will be exactly equal to AIJ EIJ minus AJI EJI. So, now all these elements must be there inside I, okay, all this must be there inside I. So, now that implies immediately that, so you can actually just add them, and because Aij being non-zero, so that implies immediately Eij inside I. So, now for this pair Ij, I not equal to j, we have that this Eij inside I. Okay. So, we have a pair Ij where I not equal to j and Eij is in I. Now, using this, it is immediate that one can prove that Eik must be there inside I. So, because Eik is nothing but Eij comma Ejk, and this is there inside I for all k, you can take it to be not equal to Ij. So, now using this, you can immediately see that EIL must be inside I for all L which is not equal to I. Okay. So, slowly what we are going to do, we are going to actually say that all this Eij I not equal to j must lie inside I. So, now I is not contained in the C times identity. So, I must be containing SLN, that is what we are trying to prove. So, we want to prove that the basis element must lie inside I, the basis element of SLN. So, now we have proved so far that Eij is there for some tuple Ij. Using that, we proved EIL is there for all L not equal to I. So, now let us look at EKL. So, this is going to be EKI and EIL, and this is going to be inside I for all K comma L, such that you can choose K is not equal to L and L is not equal to I. So, as long as you choose L not equal to I, this element is going to be inside I, and if you hit it with any EKI, it is going to be there inside I. So, that is why you get EKL for all K not equal to L. So, now it is not hard to see that again this minus 2 Ki is there. So, now what we have EKL is inside I for all K not equal to L and L is not equal to I. That means EKL is there for all L not equal to I. Okay. So, now we need to still show EKI is there for K not equal to I, but this is nothing but okay, minus 2 of EKI is just the bracket, you have to take the double bracket EIK EKI with EKI, and this is in I, and this is true for all K not equal to I. So, now using these two, you can you can easily see that E k L is in I for all k not equal to L. So, one set of basis elements of SLN lies inside your I. Now, the other set which is HK, which is nothing but EKK minus EK plus 1 K plus 1, and it is easy to see that this is also again there by doing this simple computation. EKK plus 1 and EK plus 1 K, the bracket of these two will be exactly HK, and this is there inside your I again. So, this means all the basis elements of SLN are there. So, that implies SLN is contained in I. So, now we assume that I is not contained in the one dimensional space spanned by the identity, and that implies that I is contained inside SLN. That is what we proved. Since SLN has codimension 1, so I must be either SLN or GLN. So, that is what it implies. So, this implies I is either SLN or GLN, and this completes the proof of this theorem. So, that actually asserts that all the ideals of GLN are nothing but either 0 or the center or the derivative algebra or GLN itself. So, now using this one can immediately conclude that the structure of SLN and of course, GLN. Okay. So, GLN as a Lie algebra is isomorphic to SLN direct sum the one dimensional center. So, these kind of Lie algebras will be called what is called reductive Lie algebras. So, we will actually define and give some characterization of reductive Lie algebras later, but anyway that is not important for this course. So, let us leave it. So, now as a corollary we have the following result. So, SLN must be simple, is a simple Lie algebra. Again it is just a one line proof. Let us start with I being ideal inside SLN. So, let us start with the non-zero ideal. Okay. So, now I commutes with this IN, okay, because IN being identity matrix. So, I must commute with this one dimensional space, and this implies that I must be ideal inside GLN as well. Okay. So, I is ideal inside GLN because GLN is nothing but SLN direct sum the one dimensional space CN. Now, we know all the ideals of GLN. Since I is non-zero ideal of GLN and I is contained in SLN, that force that I must be SLN. There is no other option. Okay. So, this proves that the only ideals of SLN are 0 and itself. That proves that SLN must be a simple Lie algebra. Okay, this actually tells everything about the structure of GLN and SLN, and with this actually we will develop the representation theory of GLN and SLN from next class onwards. I will stop here. Thank you.